invertible. If we say a particular S box is invertible, then we should note that the number of inputs what they are providing to the S box are exactly same with the number of output bits. Okay. Now we'll see about the next important component, that is exclusive OR. So we know about exclusive OR operation. We know about exclusive OR operations. So an exclusive OR operation mainly we use in the cryptography or in the block cipher because of its five properties. Five properties. Those are closure, associativity, commutativity, having an identity element, having an inverse element. So what does the closure property says? So if you take two n-bit words, and if you apply XOR between those two n-bit words, again the output that we are getting will be n-bit only. We are getting n-bit only. That's why the exclusive OR is having the closure property. So let us consider if I have input as 1 0 1 0, if I apply 1110, the second input is 1110. If I apply an XOR operation between these two, what will the output? So 0 and 0. So it is 0, 1 and 1, 0, 0 and 1, 1, 1, 1, 0. So what is the size of the output? It is also 4. So that is the closure property of XOR operation. So how much size of the inputs it's taking, the output is also same size. Okay. It is also having an associative property. This property allows us to use more than one exclusive operation in any order within the block cipher. We can use many number of exclusive OR operations within the same. So if we apply X exclusive OR with Y exclusive OR Z, it is equivalent to X exclusive Y whole exclusive OR Z. So both are same. Here both are, or both produces the same value. Both produces the same value. So that's why this property helps us in the block ciphers. Next is what? Commutative. That is exclusive OR Y or Y exclusive OR. Produce the same. So I'll take the same example. I'll take 0 1 1 0 with 1110. Next, I'll apply exclusive OR between 1110 and 0110. Okay. Now what is the output here? 0 0. It is 0. So what does the exclusive OR accept? When you have two different outputs, two different inputs, the output is 1. If you have same inputs, the output is 0. So I have same inputs, output is 0. Same inputs, output is 0. Same inputs, output is 0. So if we're having different outputs, the output is 1. Okay. Similarly here, same inputs 0, 0, 0, 1. If you observe, I got for this X exclusive, I got 1 Y exclusive or also I got X. So this is commutative property. It allows us to use exclusive OR in the cryptography or within the block ciphers. Existence of identity. Existence of the identity element for the exclusive OR operation is an n-bit word that consists of all zeros. All zeros. I told you, no, if you have two values which are having same, and if you have two zeros, if you consider the same example that we have considered, so 1 1 1 0 0 1 1 0. Now, so when you are taking 1, we doesn't know whether the value will not be same or not. But if you take the second value as 0, the output is 0. The output is 1. So what is 0 is doing? 0, when you apply 0 as a second input, it is producing whatever the first input, it is will be the output. So here the first input is 1, I am XORing with 0, I am getting 1. Here the first input is 0, I am XORing with 0, I am getting 0. So when you are XOR an X value with an second input as all zeros, you will get the output as X only. You get the output as X only. These are all zeros. That's what we are having an identity element. That is how the exclusive OR provides the property of identity. So the identity element for the exclusive OR operation is an n-bit word that consists of all words. If I apply this n-bit word with an n-bit input, the output will be the n-bit input. The output of the n-bit input. So existence of inverse. So each word is the additive inverse of itself. Why? Because if you apply an exclusive OR between two same elements, you will get as 0. Right? So apply between same values 1110 110. Now, what is the property of XOR? I told you, if we have both the inputs as same, the output will be 0. So as we are taking the both inputs as same, so the output will be 0. So that's why every element is inverse of itself. Every element that we are considering within the XOR operation, it is what? It is the inverse of itself. Now, if we consider a complement, so what is a complement? So how we are going to convert the complement? Simply, if we consider X as the input, we consider X as an input, we're going to represent its complement as X bar or X dash. Now, how I am going to get X bar is all the values in the zeros, all the values in the X, that is all zeros are converted to ones, all ones are converted to zeros. All ones are converted to 0, then I'll get the X complement. If you apply an XOR operation between X and this is X bar, if you apply an XOR operation between X and complement of X, then the output will be all ones. The output will be all ones. Okay, so let us check it. So if we consider 1100, 1100. Now, how I am going to get its complement? As I told you, no, simply convert all ones to zeros, all zeros to ones. So it will be 0, 0, 1, 1. So if I apply XOR operation between 0, 0, 1, 1 and 1, 1, 0, the output will be all ones. So because these two values are different, these two values are different. So it will be 1, 1, 1. So if X is the complement of X bar, if X bar is the complement of X, then the following two relations hold. That is X exclusive or X bar equal to 1 and X exclusive or once equal to X. Okay. So this is what complement operation on XOR operation works. Now, let us check whether this complement XOR operation will have an invertible or not. Whether, let us check this XOR operation is invertible out. So inverse of an exclusive OR operation can make sense only if one of the inputs is fixed. Only one of the inputs is fixed. So what are the input we can fix in encryption and decryption is, or in the block cipher is, I told you, when we are using a block cipher, K value will be fixed. K value will be fixed, right? I told you, so maybe this plain input that you are taking is plain text, ciphertext. Here we are applying ciphertext and we are getting the plain text. Those two I cannot fix, but the key that I apply, I'm applying on the encryption is same. The same key I'm applying on the decryption. So according to the XOR property, if one of the input is fixed, if one of the input is fixed, then the XOR operation is invertible. So if I take Y is equal to X exclusive or K exclusive or K, then I can take X is equal to K XOR Y. K XOR Y. Okay. So for example, if one of the inputs is the key, which normally is the same in the encryption and decryption, then an exclusive OR operation is self-invertible. The exclusive OR operation is what? Self-invertible. So this is the proof for that one. This is the proof for that one. Okay. So always remember, the exclusive OR operation is self-invertible if we fix one input. In the case of encryption and decryption, the input that we fix is what? K. The input we fix is what? K. Now we'll see about the next component within the block cipher, that is circular shift. That is circular shift. We know about logical shift and arithmetic shift. Maybe you have studied in your DLD. I don't want to discuss about those two things. Now I want to discuss about circular shift. So if you know about shift operation, we'll have two types of shift operation. One is left shift. The other one is right shift. Left shift and right shift. For example, if you consider a logical shift, so this is the data. This is a data. So if the data is 0, 1, 1, 0, 0. Okay. If you are applying logical shift, if I write by 1 bit, so simply I'll make all the data to 1 bit and the remaining empty place I'll replace with 0. That's what we are learning in logical. But coming to the circular shift, it is different. Circular shift is different. So first I'll tell with logical shift, then I'll come to the circular shift. So consider this as the data. So 0, 1, 1, 1, 0. Now this is the data given to me. If I apply a logical shift, I'm writing as LSFT, left by 1 bit, then this data becomes, so this data will become an empty place. So it will be 0, 1, 1, 1, that's 0, 111. So the 0, this will not be available to us. The 0 will be go outside. So what is the size of the data? 1, 2, 3, 4, 5 bits. So 1, 2, 3, 4 bits. So the place which is empty will simply fill it with 0. Will simply fill it with 0. That's what logical shift will do. But in circular shift, instead of doing this 0 outside, instead of leaving this 0 outside, we'll bring back this 0 at the empty position. We'll bring back the 0 at the empty position. So again, I'll show the difference between logical shift and circular shift. Okay. So let us take a whiteboard. Right now. So consider this is example for logical shift. Okay. So I have data 0 will not give you perfect thing. So what I'll do is right. So I'll take 1. So 1, 0, 1, 0. Consider I have taken a 4-bit data. If I apply a logical shift, on this data with respect to 1 bit, what happens is decode on the left. So represented by like this left shift. So the data size will be 4 bits only. This 0 will go outside. This 0 will be go outside. Now these bits, everything will move by 1. So 1 comes here. This 0 comes here. 1 comes here. So it will be 1, 0, 1. Now, whatever the place that is emptied by doing the shifting, that will be replaced by 0 in the logical shift. But if I apply circular shift for this one, if I apply circular shift for this one, so again the data size is 4. So what happens in the circular shift is the data will not go out, the extra bit will not go out. Simply it comes back and sit in the position. Simply it comes back and shift in the position, sit in the position. So it will come to here. This will be coming here. So it will be 0, 1, 0, 1. Now we got the same. No, now we'll take another input. I'll take another input and we'll do the same thing. Okay, we'll do the same thing. Now I'll take it as 1. I'll take it as 1. Now we'll clearly see the, if I apply logical shift, so this 1 will go out. This 1 will go out. So 1 comes here, 0 comes here, 1 comes here. So it will be 1, 0, 1. According to logical shift notation, it should be replaced by 0. But according to logical shift, it is replaced by 0. But according to circular shift, this should be replaced at the end. Okay. So it will be like this. So these will be shifted. The value that we have shifted will be 1101. So this is the difference between the value difference between logical shift and circular shift. Okay. Logical shift and circular shift. Now we'll see it. So in the circular things I told you, in shifting operation, we'll have two types of shift operation. Those are circular left shift operation and circular right shift operation. If you are doing the circular left shift operation, shift each bit in an n bit work k positions to the left. The leftmost k bits are removed from the left and become the rightmost bits. So if you consider this is the data, if you consider this is the data, consider this is n bit and this is the k bit. Now you are replacing this by 3 bits. If you are doing circular left shift with 3 bits, what happens is these values will come and sit at the back. So B7, B5, B6, B3. So no, sorry. I told about this is that is actually left shift. No, I told about right shift. Sorry. Now, if you consider left shift, so we need to do left shift. So what happens is these 3 bits will come and sit at the back side of this data. So this is k bits. So this is we are applying shift left. This is shift right. So that's why I thought it this is shift right. So this is shift left. So this phi B4. So B4 comes here. So B0 B4 comes here. And I told you circular left shift, they'll come and sit in the back side. So these bits are sitting in the back side. So B7, B6, B5. So if it is right shift, this is k bits. No, what happens? This data will be moved to this side, and these bits will come and sit in the back side. So that's why. So these bits are moved to the right. These bits are moved to the right by 3 positions, and this data has come and sit in the right side. So this is what circular shift left and circular shift right will do. Okay. Now the circular shift operation mixes the bits in a word and helps hide the patterns in the original word. Here the key will be the number of shifts, shift positions, number of shift position. If you consider this is the actual data, so we can also use like this. This is the actual data. Now, if I apply, the key is what I say to my receiver that your date in the data of birth is my number of shifts I'm applying. For example, I'll take it from 0 to I'll take it from 0 to n by 2. Consider n by 2 is the max I'm taking. N by 2 is the max I'm taking. So if his date of birth is considered 10, I'll make it sum up and I'll make it to 1. So 1 by 2 is 1, I'll shift by 1. If his date of birth is some 25, if date of birth is 25, 5 plus 2 is 7. So 7 by 2, I'm taking. 7 by 2, I'm doing but 3 shifts. Now, the receiver will understand that the data that he received by him, I have done and shift left operations by 3 bits. Shift right operation by 3 bits. Now, at the receiver side, he will do shift left by 3 bits. Shift left by 3 bits. Then simply, he'll get the plain text. Okay. So we can also use this as an cryptographic technique. We can also use this as what? And cryptographic technique. So let us see it with an example. So let us have the whiteboard. Right. So this is the actual data. Consider it is 0, 1, 1, and 1. Now, this is my plain text. Consider this is my plain text. Now, consider the key is 1 between sender and receiver. That is 1 shift left. If I do shift left at the encryption right, I should do shift right. If I do shift right at the encryption right, at the receiver side, I need to do shift right. So let us do circular shift left here. So if I do circular shift left, writing the circular shift left. So if I do circular shift left by 1, what happens is this data becomes 3110. So this data will be gone to the receiver. So at the receiver side, what is the data I have received? 3110. Now what you need to do, you know about the key. Now we need to exactly do the opposite operation. That is circular shift right. Circular shift right. So now if I do circular shift right, this data becomes what? So y1, so it will be 3110. Now this is my plain text. So this is my cipher text. This is my plain text. So this is my ciphertext. What is the key? I have used number of shift operations. I have used the number of position by which I need to do the shift operation is my key. So this entire thing can be considered as an cryptography technique, symmetric cryptographic technique. Okay, so we can also use these things for the cryptographic techniques. So as we have seen here, we can say that circular shift left or circular shift type, that is totally circular operations, are invertible operations. Why you are doing, if you are applying circular left at the sender side, if you apply the quite opposite circular right on the receiver side, the data that we are getting is invertible. So coming to invertibility, a circular left shift operation is the inverse of the circular right shift operation. If one is used in the encryption cipher, the other can be used in the decryption cipher. I told you. Now, next is swap operation. The swap operation is a special case of the circular shift operation where k is equal to n by 2. This means the operation is valid only if n is an even number, because left shifting n by 2 bits is same as right shifting n by 2 bits. This component is self-invertible. So this is how we are going to do the swap operation. Okay, so we are taking here B7, B6. So what is 1, 2, 3, 4, 5, 6, 7, 8 bits is the data here. I am doing it n by 2. So I am taking the n by 2. I am doing here left shift. I am doing here the left shift. So I'll take the same data here and I'll do the right shift here. So simply it is called swap. The left half is done here. The right half is done here. The left now here in the description. In the decryption phase, here the right part is made as left part, the left part is made as right part. Simply swap operation. So here we are dividing it in n by 2. Here the left part is done to right part. The right part is mapped to left part. At the receiver side, the right part is mapped to left part, and the right part is mapped to left part, and the left part is mapped to right. This is what happens in the swap. So split and combine. So split and combine, the two other operations found in some block ciphers are split and combine. The split operation normally splits an n-bit word in the middle, creating two equal length words. The combine operation normally concatenates two equal length words to create a n-bit word. These two operations are inverses of each other and can be used as a pair to cancel each other out. So if one is used in the encryption cipher, the other is also used in the decryption. So we can say that these two operations also invertible. Okay, so in this lecture we'll stop with here regarding the block ciphers. Now in the next class we'll start with the product ciphers. In the block ciphers only we're going to see about product ciphers. We are going to see about diffusion, confusion, and then we are see about Feaster cipher structures, and then we are seeing about stream ciphers, the other modern cipher, that is stream ciphers.